Hello everyone. My name is Shahheet. You can call me Heat or Shahheet, whatever you feel comfortable with. And we are going to be talking about maths. So that's the basic gist of the class is going to be about two different topics. The first topic that we are going to sort of glance over is about complex numbers, and the second topic is going to be in the later part of this series is going to be about calculus. So these are the two topics that I feel that are going to be really challenging because of what people perceive them, but we are going to talk about it in more of a simplistic and what how can it be done easily. That's the sort of plan. So this is the slide. So this is the first prize that Katie told about. It's the Domestica sponsorship prize. So it is based on attendance, and the first place is gonna get 1 year worth of subscription, and there is similar second places for 6 months, and the third place is going to receive the special notebook. So these are the prices that is there. There's personalized prices more about the interaction. So whoever like has better interaction and whoever feels most comfortable is the one that I feel will get it. So now we start with the topic. We'll start with what are number systems in general. So when we start with this is the basic chart of what real numbers are or what generally people know numbers to be. So how does this begin? So if we start, it begins with the natural numbers. So the progression of mathematics is not, that it all came into existence and now we are learning it. It's basically we saw a problem and we defined more rules to solve that problem. So the basic gist was about problem solving. So during the caveman times, natural numbers were invented because it was useful to count how many people are present in your herd. So basically, it started with self-preservation. Why, how many people are present, and that's how natural number counting numbers began. Then we saw move forward. We saw like we started doing trading and agriculture and all that sort of stuff. Then we realized that there is a possibility that nothing can exist. So we introduce zero into the system. Then then we also move forward. For example, during trade, if you give out something and you get nothing in return, so you will get net negative effect on your end. So that is where during the barter system we get the existence of negative numbers. So basically line of credit is where the negative systems or negative integers got introduced. Then we got two different farmers. One is growing bananas, one is growing apples. So there is two different type of quantity, and you need to equate them. So you ratio the numbers. So rational numbers got introduced. Basically, decimal numbers or ratio. So if you say two bananas are equivalent to three apples, so that's like equivalent ratio of them. Four bananas will be equal to six apples. That sort of mindset was with the rational numbers. Now, in the irrational side of things, it started with the question of what is the square root of a particular number. Yeah. So how it started was in irrational numbers, we find equations that were, you know, this sort of situation or this sort of situation to be precise. These are the equations that exist. Like, so for example, this is an equation. There is a solution for this. If we go by realistic methods, what will be there? The You guys do know the like. Let me first then share this. The even any quadratic equation is solved, we know the values of x for which it is 0. So the values are specifically minus b plus and minus square root of b square minus 4ac upon 2a. This is the solution of a quadratic equation. So this is where we introduce complex numbers or imaginary numbers into the thing, because there are equations that are x square plus 1 equals to 0, for example. So what will be, yeah, the x square equals to minus 1. This is the situation we haven't really saw before. So this was a question that, arose a lot because a lot of equations didn't have any solution. So like there is this famous equation, we'll talk about it later as well. It is x cube equals to 1. So we know that one solution of this is 1, but there are two other solutions as well that aren't in present in the real graph of the x cube function, or in general we don't see them, right? This is the part where x square equals, so the other part of this equation will be x square plus x plus 1 equals to 0. These solutions are also really important in some sense. And this is the sort of questions that, we didn't have an answer present to, because there was no number which you can square to get a negative number. So that is why we introduce a concept called iota, which is equals to square root of negative 1. It is defined like this. This is what gives the complex number their meaning. This is basically what complex numbers are. Now a little bit of a definition. So complex does, if we remember set theory, the generalized set theory function is natural numbers are a subset of whole numbers, which are a subset of integers, which are a subset of rational numbers, which are a subset of real numbers, which are a subset of complex numbers. So all real numbers are part of complex numbers. So any real number is also a complex number. That is one part. And in complex numbers, there are two types of numbers. So one is purely imaginary, that has no real component present to it. So it is just iota into some number b. B can be anything. It belongs to R. And the other is mix, that is A plus iota B, where A and B both belong to R. If it has a real component and a complex component, it would be a mixed complex number. If it is just a imaginary number, then it is called a purely imaginary number. Now, the term imaginary might confuse people with it being in the sense of it is not real world application. It started with imaginary as a terminology because when at the time it was being discovered that this sort of number system or this sort of arithmetic also exists, it was considered bizarre to have a number that squares itself to be a negative number. Hence, it was called an imaginary solution to the equation. We just force the solution basically onto the uh, question. If it's basically like saying that if x square equals to 1, we are saying x equals to a is a solution. It's basically not actual answer to the question. That's what it was thought. But later, with the advancements of physics, we saw that it has very important real world applications. It can be seen. So complex number pop up in the most fundamental theories we have. So they pop up in the Schrodinger equation that explains what a wave function is, which essentially what everything is made of. So every proton, neutron, everything is given by this wave function, which is minus one of the field. So this is the sort of reason why complex numbers are now really important and really well needed, or they are researched more. The other part is they help a lot with wave mechanics. We will talk about this later as well. It is about the complex plane. So this is the real line. This is the imaginary line. So this is the complex plane of number. Just like how we do in Euclidean geometry, we have a x coordinate and a y coordinate. This is the same as that. So this is the complex plane of numbers. So when we say a particular, let's take an example of a particular complex number called 3 plus 4 iota. 3 plus 4 iota, right? So that number can be represented in many ways as well. So there are four basic representations that we use. So for complex numbers, there are four basic representations. First is the polynomial. That is basically a plus b iota of the form. So it is 3 plus 4 iota. This is the polynomial form of the complex number. There is also the polar form of the complex number, where we basically convert the number into, like, the variables a and b, they get converted into r and theta. The polar form of the number, it basically is converting it into a trigonometric function. It is r cos theta plus iota sin theta. This is the polar form of the same number. Then there is the Euclidean form of the number, that is r into e raised to I theta. Yeah. And then there is the planar form. That is what we are interested. So when we say it as a graph, this is the real part, this is the imaginary part. Now this is 3 plus 4 iota. So it will be a point, basically how we do in coordinates. It would be 1, 2, 3, 1, 2, 3, and 4. So it will be a point here. So these are the four different ways of representing the complex number.
Because I've typically done like calculus in Euclidean form. So what do you use polar form for? Because I haven't seen that before.
So that is basically used where we want to use wave functions or wave properties of a function. So for example, if there is a function that is cos theta plus sin theta or that sort of thing, it, it is used when we use uh, wave spectrum of a. So I can give you an example where our cos theta plus iota sin theta is used. It is when we, in the wave mechanics, or when we are working with radio waves or microwaves or anywhere in electrical signals, AC signals, right? Wherever there are signals, we have a big tool called Fourier transform. So Fourier transform is a big tool that is used in wave related property. In that, uh, it is really important sometimes to use the polar form of cos theta plus sin theta. So the example would be where there are like three audio waves that are being combined because all of them are going through microphone, and you are hearing only one on the outside because you have an suppressor in between, a software suppressor. So what that suppressor does is, because the three waves are going in combined and you don't know which wave is present, So the actual graph will look like something random, right? It will be periodic, but it will be random. But so the what the suppressor does is it breaks it, or what rather what Fourier transform does is it breaks it down into a sum of sine waves with different frequencies
So
that are
Polar waves
overlapping.
are used for like looking at like, I guess cosine or sine or tan like,
Yeah,
like
polar is
curves. Or, okay.
basically useful. Yeah, polar is basically useful where we are talking about uh, periodic functions that are present. So multiple periodic functions. So let's say there is a particular wave that is sum of three or four sine terms. Then it is beneficial to use polar form of the uh, complex number or the number. Like polar forms are basically used when there are waves or phase involved. So the for like the term generally used in engineering or further is phase instead of waves. It's called the phase of the term. So phase is when there is a angle present and something is rotating. That's where phase is introduced. So for example, if there is a rotating motion or an oscillatory motion, that is where you can use polar form, because it if it is oscillatory you can break it down into sum of sine and cosine. That's why it is used. Is purely imaginary a case of mixed numbers where A is real? No. So purely imaginary is a complex number, but it is considered a purely imaginary. Mixed numbers are basically when A is non-zero. But yeah, you can sort of say it is a subset, but it is not considered to be part of mixed numbers, if that makes sense. Mixed numbers are considered when A is non-zero. So the main reason we study complex numbers is basically almost everything that is working on your phone uses complex numbers in some way. The microphone uses complex numbers because it suppresses a lot of noise, and it uses Fourier transform, which has imaginary numbers and complex numbers baked into it. Then there is a lot of image related systems that uses diffusions. So that diffusion is done using matrix multiplication that is done by complex numbers. So complex numbers are really useful when it comes to computing, because when we see real when we see that a real life signal is meeting a digital signal. So almost all real life signals are analog or continuous in nature. But our computers are really, really fast with digital signals. They can't really work with analog signals because having a continuous graph is meaningless in a computer. At a point, you are just taking dots in a computer. For example, a sine wave in a computer is not a particularly a continuous wave. In a graphing calculator or in any computational devices, you leave after a particular point as a step. So it is basically short steps like this instead of a continuous wave that goes like this. So this is where there is a conversion between continuous and discrete. That is where complex numbers are used. It is also present in one of the most fundamental theories we know, that is the Schrodinger's theory of wave motion of an electron. So now this is the types of representation that we talked about. So now where they are used. So the polynomial one is used when we are just wanting to represent or just want to talk about the complex numbers in general. The polar form is used when there are waves present, and the Euclidean form is used when there is a gain or a particular multiplicative property being applied to the number. So it is easier to square the number in that form if you see. So if we want to square, let's say a plus iota b, what would it become? It would become a square minus b square plus 2 iota ab, right? And if we square this number, it is just r e 2 theta. So this is why it is important, because this one is easy in multiplicative situations where there are squares or cubes or nth power present. So I can explain in the polar form. Let's say this is so sine theta plus iota cos theta is actually a circle, the unit circle. Any point, this is theta. Then it maps out a circle. So R represent the radius of the circle. Because if it is just sine theta plus iota cos theta, it is a unit circle where R is 1. In general, R represents the radius of the circle. That's why it is used as R. In the Euclidean form, it is considered the same because the identity that e raised to iota theta equals to cos theta plus iota sine theta. This identity is used multiple times to convert between the forms. So, for example, if you are given a wave and you want to multiply it with something, then you won't square this one. You will convert it into this form, multiply it here because it is easier, and then convert it back into this form. That is why this formula is very useful, and hence it is used R in both of the forms. There is no particular reason for Euclidean R. It is just due to convention as it is common. So the next topic that we can talk about is what are conjugates of a number. So when we talk about conjugate, so having the same real part and a different or the opposite imaginary part is called the conjugate of the number. So 3 plus 4 iota, its conjugate will be 3 minus 4 iota. This is the basic definition of what a conjugate means. It's basically if a number z, this is the variable we generally use to represent a complex number, it is z. And if it is a plus iota b, then z conjugate, this bar represents its conjugate, that is a minus iota b. This is the basic definition of what conjugate means. And why it is important to have a definition for this term is because of how complex numbers generally come into play. So if you are looking for a solution to a quadratic equation or any equation in general, there is not a single answer. Never. It always comes in pair of z conjugate because there are because this if there is a equation in which a plus iota b is a solution, then a minus iota b is also going to be a solution. That is because if you square both of this term, the real part of this equation is same because plus iota square and minus iota square, they are going to be same. So the real part of both of this term is going to be same if there is any equation you put it in. Where the catch is going to be that let's say this is the equation, right? Then a b c, if all of them are real numbers, like the equation should be a real equation, then the solution is always going to be in a pair of two conjugate numbers. It can never have two different numbers as well. So now there are also two terms regarding a complex number, that is modulus of the complex number and the argument of the complex number. These are the two terms that are properties of a complex number. So the modulus of the complex number, or the real impact of the complex number, it is considered to be square root of a square plus b square, where the number is a plus iota. This is the modulus of the complex number, and the argument of the number is, it's basically the angle it is forming. If we see in the planar form, the argument is the angle that it forms. This theta is the argument. Now the definition is weird as to what defines the theta. So for argument, it must belongs to minus pi to pi. So if it is a number present here, then you will measure it this, and it's a negative argument. That is the sort of key difference. So how do we add and subtract or multiply them in future? So addition of complex numbers, it is basically all algebra is similar to how we solve linear equations. So if there are ax plus by, right, all algebra is similar. Iota in all sense is going to be a separate variable. So algebra is all going to be similar. So it is basically, if let's say this is a number and another number is 4 plus 5 iota, then the addition will be, we add the imaginary terms and we add the real terms separately. So it's basically 7 plus 9 iota. This is the addition. Same with the subtraction. For multiplication, it is basically normal multiplication of numbers. So it's basically, let's say we do a into, so it will be 3 plus 4 iota multiplied by 4 plus 5 iota. It's basically going to be 12 plus 15 iota or 16 iota minus 20. So it's basically minus 8 plus 31 iota. This is basically the multiplication. And for division, what we do is, this is where the properties come in. Let's say you want to divide the numbers. What can be done here? Now, let's say for division, we use the modulus. So modulus is also this thing. If we see z into z complement, that is also a specific number, right? A plus iota b into a minus iota b. Let's multiply it. It will be a square plus iota ab minus iota ab minus iota square b square. So this and this get cancelled, and it's basically a square plus b square is z into z conjugate, right? So it's modulus of a number, of a complex number, is basically square root of it into its conjugate. This is the property that we use for division. So what we do is, let's say we want to divide we want to find the reciprocal of the number. So let's say 1 over z. So what we do is, we multiply both top and bottom with the z conjugate. So it's this, and now it becomes basically z conjugate upon square root of mod z square. So it's basically z 1 by z is equal to Z conjugate upon mod Z square. This is the way we reciprocal the numbers. So what we do in division is you find the reciprocal of the number and then you multiply it with the second number. So let's say if we want to do Z1 by Z2, what we do here is Z1 into Z2 upon mod of Z2 squared. That is the solution we go for. Z1 into Z2. So this is the complex multiplication we can do, and this is just a real number division. So basically, it's a division of the overall term. So we can do a few examples here as well. So maybe you guys can uh, get the answer. Let's see who gets the answer first. So it's the same two numbers, 3 plus 4 iota divided by 4 plus 5 iota. This is what we have to solve. So let's multiply it. It would be 3 plus 4 iota into 4 minus 5 iota divided by 4 square plus 5 square. I doubt that is correct, Artemis, because 4 square is 16 plus 5 square is 25. So we are looking at like 14, 41 in the no, then you didn't have to. So the mod is square root. So you just had to put 41 in the bottom. And if we see the top part, it would be 12 plus 20. Now it would be 16 minus 15, so plus iota. So yeah, I think with the exception of the squared 41, you got the right answer. It is basically as same as a plus b into a minus b is equal to a square minus b square. It is same because iota is present, the minus becomes plus. Yep, you got it. I'm sure. So that is basically the algebraic part of the thing. So now if we see, uh, there is a bit of a complex, a little bit challenging thing. That is, let's say you are given the number z is equal to 3 by 5 plus iota 4 by 5. Or even let's make it easier for the first time. It is root 3 by 2 plus iota by 2. Okay, that is your number. And you need to figure out this solution. Let's say, for example, we need to do this thing. Okay, this is the question that is proposed. What is the value of this? So we will use a property here. Like we will solve it without the property, but later on we will just do it as a generic proof. It is basically we will start with this number seems a little familiar, right? The terms are said to be like it looks like cos theta equals to root 3 by 2 and sine theta equals to 1 by 2. It's like the values are looking very trigonometric, right? So it is a question about polar form and its properties. So what we can do is we convert this set into into its polar form first. So R will be 1 since it is basically a unit circle. Now theta comes out to be pi by 6 or 30 degrees. Like the angle value comes out to be 30 degrees. It's If you don't know trigonometry, then it is a fact that cos theta equals to root 3 by 2 implies theta equals to pi by 6. That sort of thing. If you do know, then yeah, it is a generic answer that yeah, 30 degrees is the angle at which cos theta is root 3 by 2 and sin theta is half. So what we do now is we convert, so z is now cos pi by 6 plus iota sin pi by 6, correct? This is z. Now we can try z is equal to e raised to iota pi by 6, because we saw before if it is cos theta plus iota sin theta, then it can be converted into e raised to the function. Now we can do the, here we can see how different forms are very helpful. So basically now z raised to 1000 can be easily done as this. It becomes very easy to compute this number instead of doing z raised to 1000 on this number. That is why we convert into different forms. Now we can see this is 500. Now if we convert it into cos 500 pi by 3 plus iota sine 500 pi by 3, it it can be broken down. So it's basically now trigonometric identities and not about complex numbers, the question. So if you know trigonometry, then you can here put put out as we divide 2 pi as a different term. So it's basically 500 minus pi by 3, 167 pi. It is 167 pi minus pi by 3. So this is the term. 500 pi is basically 167 pi minus pi by 3. Or so, or you can say 166 pi plus 2 pi by 3. Now the 166 pi is goes to 0 because in cos and sine after 2 pi the values repeat. So it's basically a trigonometric question now. So now it becomes cos 2 pi by 3 plus iota sine 2 pi by 3. And we can solve further with this one. If you know trigonometry, then yeah, this question becomes easier. Now if we had to do raise to 1000 power of this number, then it would be, then it becomes really challenging to raise this number to 1000 power without going into this form first. So that is why we have different forms of the numbers. This is what I had planned right now. For the next lecture, it would be more we talk about what a complex number means in terms of vectors and space. So from the next lecture onwards, it would be more about the graphs of the function. So I can give you a hint or what it will be about. It will be basically saying that if we take any line or a vector and we multiply it with iota, it is a 90-degree turn. Yeah, this is basically what we are going to talk about in the next lecture. Why is it a 90-degree turn, or how is it a 90-degree turn? And what are the implications of that? That's what the next session is going to be about. It's about complex numbers. So it's basically we had an introduction to what are complex numbers. In today's session, we had what are complex numbers, what is the real life applications of them, where they are used basically. Then we talked about so yes, we had the what are number systems first. We start there, like how did numbers evolve. Then we went on to complex numbers, what particularly gave rise to complex numbers. Then we came to what were the real life applications of complex numbers. What are the what are actual real life things that you use? For example, GPS is a thing in which complex numbers are used. That sort of thing. Then we what are the types of representation of a complex number? So it's basically there are three, and a fourth called the plane, like the complex plane, which we will talk about in next lecture. Then it is about conjugates. We talked about conjugates and what are the meaning behind having a conjugate of a complex number. Then we talked about uh, what is the argument and what is the modulus of a complex number. And then we did a few examples on algebra of the complex number, basically addition, multiplication, that sort of thing.